And one of our latest works involved this nearly cosine or in general trigonometric function and Jinc functions. In general, I really take care of applications of these special functions for physics from theoretical to experimental physics. So in fact, our work that is already lasting from several years together is really a joint work where uh, we are really trying to develop some theory of this special function, but then also we find some application for physics. So today I speak about nearly cosine functions, defining them, and also I will speak of the umbral images of this function that can be useful to solve some integrals that involve this function. So you may understand that especially in physics, but not only, of course, we can model the nature by the help by means of mathematics, but very often we need to integrate very difficult formulas. Of course, we can use calculators, but there are still some techniques like this technique of umbral method that can allow us to solve very complicated integrals, finding exact solutions, and this means that the simulations that physicists do of the nature may be really uh, we can really made faster. So also I will speak of Jinc functions and some application, and then I will give some conclusions. So concerning the Euler-Nearly cosine, we have this definition that is similar to the definition of a cosine, but instead of the factorial, we have this Pochhammer symbol. And in general, it's possible to notice that for m equals 0, this is the series that identify the cosine, the normal cosine, the trigonometric cosine. So actually, this is a kind of generalization of cosine function. But what we have noticed also is that we can find an umbral image that is of a Lorentzian type of this kind, uh, which has this expansion, and this operator that we define for the umbral image, we define it as acting on some abstract quantity that we call vacuum. This is in analogy to physics also. When in physics we used to create and annihilate states, quantum states, in this way. And this, let's say, creation operator has some algebra of this kind when we combine two of them close to each other. But the important thing here is that we can move the dependence upon x from um, let's say from the cosine to this Lorentzian function. And this helps us, for example, in solving some integral, because if we represent the cosine, the nearly cosine, in terms of this Lorentzian function, we can, for example, solve this integral quite straightforwardly. And so you see that we have used an alternative abstract representation of this cosine. We have solved the integral, and then we have applied the solution of the integral to this abstract quantity that we have called vacuum, but we know the algebra of this operation, because we know how the operator key has to act on the vacuum V0, which numerical result must give. So in the end, we can solve very complicated integrals, because this integral for any kind of m larger than 0 is not easy to solve in general. But with this kind of method, we find a general solution that is quite simple. And about this function, we can see that they have some similarities with normal cosines and sines, because um, we will see especially the similarities, but in this case, actually, I'm showing some differences because you see that if we take the derivative of cosine m, so of the nearly cosine, the first derivative is not equal to what we can define as the opposite, so minus the nearly sign. So if we define the nearly sign in analogy to, so starting from the series where we replace the starting from the Taylor expansion, replacing the factorial with by the Bochhammer symbol, we can define a generalized sign, but this is not equal, or anyway not straightforwardly related to the derivative of the nearly cosine. So in this sense, they are different from normal cosine and sine. We show some plots of the nearly cosine for m that is not integer, so it's 1/2. And so actually it's cosine, the red one, and the sine, the blue one, and also for m equal to 5. So also here you see a very strong difference. For larger m, you pass from something oscillating to something that is having, let's say, half an oscillation in some sense. So in general, since these two cosine and sine general and quasi nearly cosine and sine are different from normal cosine and sine, they will have different parametric plots. This is the case for m equals 0. So the parametric plot um, for cosine and sine, normal cosine and sine, and then we have for different values of m. So for m equals 0.5 here in the center, and for m equals 2 here on the right. And basically, for example, there is a very classical problem in physics of the harmonic oscillator where the phase space, we call it phase space of the particle, is of this kind. So the position and the velocity of the particle, if plotted versus the time, they are related like this in the space. So the energy of an oscillator is conserved, so the system is closed, is stayed closed. And this happens for normal cosine and normal sine. So when the position is of this oscillator is described by a normal cosine and the velocity by a normal sine, except for a sine. But here you see that for larger m, we have actually non-conservative system somehow. So we can really think that these things can be related to different physics. This nearly trigonometric function for larger m. This nearly cosine function is also related to an hypergeometric function. So it's something that somehow is already known in this sense. And so if related to some known function that is the hypergeometric function of this kind. But also we can find analog of the Euler formula because we know that normal cosine and normal sine can be expressed in terms of imaginary exponential functions. And if we define a suitable imaginary exponential function nearly quasi nearly imaginary exponential function, we can generalize somehow these formulas that are really useful, especially in physics, for describing normal cosines and normal sines. So these are very much useful in solving differential equations, like for the circuits, electrical circuits, and many other things. So in the end, um, it's nice to see that even for m larger than 0, we can find this kind of properties. So there are some similarities and some differences between the nearly cosine and the normal cosines. We also have worked on some generalizations of these functions. For example, here you see that we generalize somehow this umbral representation because we put an exponential parameter nu here. So for nu equal to 1, we get again the definition of normal of nearly cosine, if you remember. But in general, we can define another abstract function that has actually this representation, integral representation. And this representation really again helps to solve very complicated in principle integrals, finding a closed expression. Now, for this function in particular, we didn't study applications, but in general, we will see in the future if this can be useful to for something in physics, for example. But another generalization is this. So where we don't consider the square of the operator here, of the operator key, but just key, and then the square of x. So it's still a Lorentzian, but just in x, not in key x. And this modification of the quasi-cosine, of the nearly cosine, is related to Gaussian functions, because you see that for m equals 0, we get the Gaussian function. Not the cosine, but the Gaussian function, just changing key square into key. And then we have different plots for different m. So about applications of nearly cosines, we were thinking about some application to free electron laser because, of course, Pino is very much expert in this field, and I also work actually partially in this field. Basically, you see some specific expression of the quasi cosine. You have cosine, nearly cosine with m equal 1 is actually sinus cardinalis. So it's a function that is really representing in physics absorption resonances or resonances in general. Here, for example, we have line shape of the free electron laser. So this is a resonance in the spectrum that is emitted in this kind of radiation devices. So we have that this free electron laser can emit very narrow band radiation, and this is represented by this kind of function. So some distribution that says that the most of the photons energy are around a central value, and this distribution is quite narrow. So also the gain is important in free electron lasers. So we have some frequencies are um, obeying to some the frequencies obey to some gain law in this radiation device where light is amplified. So I remind you that laser, it means light. LA stay for light amplification. So in the end, you have some gain in this device, and the cosine, the first derivative of the quasi cosine is exactly related to this. So why we are saying this? Because we have to, of course, go deeper in this, but this kind of function may ease the analytical description of these systems. And also, we have found some potential in some potential application to molecular physics, in molecular physics. Because with a slight modification of the function that we defined earlier, we can find this kind of new function. So with this parameter 1/2. And this function is very similar to centrifugal potential. So you have that when molecules are attracting each other, they feel some long range attraction. Or in general, when two bodies, for example, even in the atoms or planets, they attract each other, for example, through Newton law, through Coulomb law, so electrostatic, gravitational law. But in general, if there is some initial velocity, and so some, we say, angular momentum of these particles that are possibly going to orbit around the center, then the attraction potential, the effective potential of attraction is modified by this rotation around a center. So in the end, when we have a body that is orbiting around another body, the effective potential, the effective attraction energy with the distance has this shape, and that's why there is also a region of stability where the energy is negative, so it means that a bound state is created, so an object is really orbiting around another. Otherwise, the two objects would just repel or attract uh, without any stability. So this kind of function may be used in these fields. Also, an interesting aspect of nearly cosines is this, that they obey to Kramers-Kronig relations. These are causality relations in physics. So where these are obeyed by some quantities like um, the that we call normally susceptibility. So when we study the electromagnetic response, for example, of some electromagnetic medium, we introduce a quantity that we call susceptibility, and then this is important because matter, so solid matter and electromagnetic matter, doesn't respond instantaneously and locally all the time to some excitation field. So if we excite the matter, matter is not responding instantaneously and in general even not locally. And that's why we introduce a response function. And this response function must obey to the law of causality, because the signals in physics cannot travel with a speed that is larger than the speed of light in the medium, in the system. So um, in the end, this susceptibility function can be modeled by nearly trigonometric function. And in fact, as this susceptibility function, the nearly trigonometric function obey to Kramers-Kronig relations. So this can be a good candidate for describing some line of absorption in some medium, because this is exactly the shape of an absorption line, in fact. And absorption line, it means that matter is absorbing some preferential photons than others, and in general, this mechanism of absorption is not instantaneous. Also, there are possible applications in quantum mechanics of this function, because they obey to an eigenvalue wave equation. So also we may go deeper in this topic, but for basically this is the equation that the differential equation that the nearly trigonometric function, in particular the nearly cosine function, satisfy. And this is corresponding to some quantum particle that is interacting with some system with an interaction potential that is here. I'm pointing to it. So we have still to understand to which physical system may this correspond, but this kind of formalism may be useful to study this quantum system, possible quantum system. And also we have worked during last year on Jinc functions. Let's say we have done similar work, but for these different functions that we call Jinc. It's known in literature also as sombrero function somehow. In general, it's this expression. This expression that also admits some umbral representation, in this case Gaussian. And this operator C as this operation rule on the abstract quantity that we call vacuum. Why we construct this apparatus? Because we can solve very complicated integrals that otherwise would be hard to solve. For example, the integral of the Jinc can be very easily solved if we use the Gaussian representation, because the integral is reduced to the integral of a Gaussian that is very easy, and then to the operation of the operator C on the vacuum. It's not straightforward that the result is correct, no, because we are kind of using a trick here, but we have verified numerically that it works. And also, this is another integral that can be easily. I mean, it's very easy to verify that this number is equal to 4. And also, this is another integral that it's very hard to solve in general, because the Jinc function is complicated. Here we have a dependence under square root, so it's quite complicated in general, and also numerically is not so easy to treat. But with this formulas, and we verify the result numerically, it's quite easy to find a closed expression in terms of a Struve function. So you see the power of this method and this description, but also just to speak about general properties of these functions. These are related to trigonometric functions because we can generalize the Jinc to some Jinc of order n. Of course, when n is equal to 1, we go back to our original Jinc. Otherwise, we have a generalized family, generalized class. And also, for example, we can solve this very complicated integral with the Umbral representation, and we see actually that this integral of the Jinc of order n is still related to a Jinc of order n minus 1/2. So there is also a relation between different Jincs in this case. But which application we have found for this function? For example, we have found application in laser physics because we have that a laser beam is radially a laser beam is radially symmetric sometimes, very often, and if we solve this integral, we can find this result in terms of a Jinc. So the laser intensity sometimes for a beam that has this structure can be expressed in terms of a Jinc function. But why sometimes the field has this shape? Because when the field is diffracted by a hole, it gets this. When a plane wave is diffracted by a hole, it gets this shape. This is the application of the Jinc function, and we can actually, once we know that this is the expression for the laser intensity, the intensity is the energy per unit time and unit surface, we can also calculate the total energy or something related to the total energy, because we can try to calculate the integral of this squared Jinc using the Umbral method. But this time there is a complication because we have two operators to be defined, two Umbral representations and two operators C1 and C2. In general, it's not straightforward to understand how C1 and C2, especially this combination that you see after the integral. You see that after the integral you have C1 times C2 divided by the sum. How this combination of C1 and C2 can operate on the vacua phi1 and phi2. But we have guessed this dependence, and we have found that guessing this dependence we find the correct result. Okay, in this case was kind of trivial in some sense, but in another case, using this guess here in the red box really helped to solve a very, very complicated integral. In fact, we also studied this problem physics, the two iris experiment. So in quantum physics also particles behave like waves. In general, if you send some particle like electron through two holes, you may expect to have, uh, let's say, the shadow of these two holes, or better, you would find on a screen after these two holes, you would expect to have two light spots if you use a scintillator and the scintillator emits light when the electron hit on the scintillator. But in the end, what you see is actually something like this, or even something like this in some cases. So the two electrons, or even the same, actually, quantum mechanics says that this happens at the level of the single electron, um, will behave like this, so with a diffraction pattern. And so in quantum mechanics, we define this problem in terms of a scattering quantities. We define a scattering amplitude, which means that we have an electron, a single electron that is traveling towards these holes. It's a plane wave, so it's defined in all the space, but then it can fit through the left hole or through the right hole. And after the hole, we have some screen. And on this screen, we will see something like what is plotted here. And this is a very famous problem that is related to the really origins of quantum mechanics. But in general, mm, what is important when we want to solve this problem is to find the wave function, because the wave function is the function that describes this particle. So the probability to find this particle everywhere in the space, and being the square of c of psi related to the probability of finding, actually is the probability to find the particles in the space, must be normalized to 1. So the integral of c squared must be 1 if we integrate this function over the full space. And in this particular example, we have that the normalization of this function comes through these integrals that I report here. So these are very, very complicated integrals because we have double integrals, so two parameters, that theta x and theta y, because in the end, we have a bidimensional screen after the two holes. We have to integrate two Jinc function with different argument, and also very complicated because it's under square root. So it's double integral with very complicated argument, and still using the same rule of composition. First of all, we use the Gaussian Umbral representation. Then we solve the integral and we find again um, this kind of structure. So C1, C2 times C2 divided by the sum acting on two vacua. And in the end, we get a closed expression for this integral, and also for another integral that is also relevant for the normalization of the wave function. So in the end, we have also compared this integral with the numerical results, and this basically the same. The result is the same, and actually this is an analytic expression, so the numerical computation is very fast. While to solve this double integral numerically, even with not the most trivial methods of numerical integration, it takes a few seconds. So it's very complicated, very slow to be computed. While we have found a closed expression thanks to the umbral representation, and also um, our guess of how these two operators act on the vacuum. But in general, so we have solved a, a very important problem in quantum mechanics, because this problem has been solved for the case of slits. For the case of irises, it has been solved, but um, we let's say this result of the normalization, as far as we know, is new. So We have presented some special function within the context of an Umbral interpretation. Such interpretation allows resolving rather complicated integrals in a smart and powerful fashion, suitable for application in physics, and we have focused on some application without going too deep in some specific example of solvable integrals, even if few of them I've shown. And also, I didn't show all the generalizations that we have discussed in these two works that we have developed recently, lately.